Somewhere in the universe, right now, something is falling toward a black hole. Long before it reaches the edge, its light will stretch, its time will slow, and to anyone watching from far away, it will appear to freeze, forever suspended at the boundary of no return. But to the thing falling in, nothing marks that boundary at all. It simply keeps falling, toward what no one can fully say. Because inside a black hole is the one place in the universe where the two greatest theories in physics, the ones that explain everything else, completely contradict each other. One of them was built by a man who didn't believe black holes could exist. His name was Albert Einstein. In 1915, Einstein published his theory of general relativity, a new description of gravity, not as a force, but as the bending of space and time itself. Massive objects warp the fabric around them, and everything else, including light, follows the curve. It was one of the most successful theories in the history of science. But Einstein never expected anyone to take his equations to their extreme. Someone did, almost immediately. In 1916, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. In the middle of the war, he found time to solve Einstein's equations exactly, for a single point of mass. His solution described something strange, a boundary in space where gravity became so strong that nothing, not even light, could escape. We now call that boundary the event horizon. Schwarzschild sent his solution to Einstein from the trenches. He died of illness a few months later, never knowing what his mathematics had actually described. Einstein published the solution, but publicly doubted such an object could ever form in nature. To him, it was a mathematical curiosity, not a real place. For decades, most physicists agreed. Then, in 1930, a 19-year-old astrophysicist named Subramanian Chandrasekhar did the math on dying stars. He calculated that any star heavier than about 1.4 times the mass of our sun could not resist its own gravity once it ran out of fuel. It wouldn't settle into a stable dead star. It would keep collapsing forever. 5 years later, in 1935, he presented his findings at a meeting of the Royal Astronomical Society. Sir Arthur Eddington, the most famous astrophysicist in the world, stood up and publicly ridiculed him, calling the idea absurd. Chandrasekhar was right. It took the scientific community nearly 50 years and a Nobel Prize to admit it. By 1939, physicists Robert Oppenheimer and Hartland Snyder described exactly what happens when a massive star collapses. It doesn't stop. It falls in on itself, past the point of no return, forever. For years, nobody had a name for it. In 1967, physicist John Wheeler gave it one, almost as a joke: black hole. The name stuck. The mystery didn't go away, because a black hole isn't just an object. It's a hole in our understanding. According to general relativity, once you cross the event horizon, there is no stopping. Every possible path in space leads to a single point. Physicists call it a singularity, a place where density becomes infinite, and the equations of physics simply stop working. It's not that we don't know what's there, it's that the math itself breaks down. For decades, that's where the story ended. A black hole swallowed everything, including information, and general relativity had nothing more to say about it. Then, in 1974, a young physicist reshaped the problem entirely. His name was Stephen Hawking. Hawking applied quantum mechanics, the physics of the very small, to the edge of a black hole. What he found stunned him. Black holes are not entirely black. Due to quantum effects at the event horizon, black holes slowly emit radiation and lose mass over unimaginably long timescales. Given enough time, far longer than the current age of the universe, a black hole would evaporate completely. And that raised a question that would divide physics for the next 50 years. If a black hole eventually disappears, what happens to everything that fell inside? Quantum mechanics has a rule that cannot be broken. Information can never truly be destroyed. The complete physical state of anything, every particle, every detail, must in principle be recoverable. But Hawking's calculations suggested the radiation coming out of a black hole was random, thermal, empty of the details of whatever fell in. If that's true, information really would be lost forever. And if information can be destroyed, then quantum mechanics itself, the foundation of atomic physics and chemistry, would be wrong. This became known as the black hole information paradox. It pit two of the most successful theories ever built directly against each other. General relativity said nothing unusual happens at the event horizon. Quantum mechanics said information cannot vanish. Hawking's own math suggested it does. Something, somewhere, had to give. In 1997, Hawking made it personal. He and physicist Kip Thorne bet against physicist John Preskill. Hawking and Thorne wagered that information is truly lost inside a black hole. Preskill bet that it must, somehow, survive. The stakes, an encyclopedia of the winner's choosing. For years, no one could prove either side. Then physicist Leonard Susskind proposed a way out, an idea now called the holographic principle. Perhaps information isn't lost at all. Perhaps it's smeared across the event horizon itself, encoded on that boundary like a hologram, before anything ever reaches the singularity inside. It was elegant, but it demanded a strange trade-off. An observer falling into the black hole would see information falling in with them, while an observer watching from outside would see that same information smeared across the horizon. Two contradictory truths, both allowed to be true, as long as no single observer could ever witness both. Susskind called it black hole complementarity. Hawking, for years, refused to accept it. In 2004, at a conference in Dublin, Hawking conceded the bet. He announced that information does escape a black hole after all, hidden in subtle patterns within the Hawking radiation itself, patterns his original calculation had been too simple to capture. He handed Preskill an encyclopedia, but conceding the bet didn't end the argument. It only sharpened it. Because if information really is preserved in the radiation, physicists had to explain exactly how, without breaking Einstein's other great insight, that crossing an event horizon should feel like nothing at all. No wall, no violence, just falling. In 2012, a group of physicists showed you can't have it both ways. If information is preserved outside, and nothing unusual happens at the horizon, the math produces a contradiction. Their proposed fix was almost violent in its implications. Maybe there is no smooth crossing at all. Maybe anyone falling into a black hole would hit a wall of extreme energy right at the horizon and burn instantly. They called it the firewall paradox. It suggested that either quantum mechanics, or general relativity, or our fundamental idea of smooth spacetime had to be wrong. More than a century after Schwarzschild first solved Einstein's equations from a trench on the Russian front, physicists still don't agree on what actually happens the moment you cross into a black hole. Some believe the answer lies in string theory, and the strange proposal that black holes and wormholes might be built from the very same quantum entanglement that connects particles across the universe. Others believe we need an entirely new theory of gravity, one that finally unifies Einstein's smooth curved spacetime with the strange, probabilistic rules of the quantum world. In 2019, humanity captured the first ever image of a black hole's shadow using a network of telescopes spanning the entire planet. We can now see the edge. We still don't know what's beyond it. Maybe the answer will come from a theory no one has written yet. Maybe it already has, hidden inside equations physicists haven't yet learned how to read. What we do know is this: somewhere in the universe, right now, something is falling toward a black hole, and the question of what happens next isn't just about that black hole. It's about whether the two greatest theories in the history of physics can ever be reconciled, or whether one of them, eventually, has to break.